All right, so our geometric definition of a hyperbola. Let's just talk through it before you start writing it down. So pencils down for a moment. Just like listen. So here's a hyperbola. It's two curves facing away from each other, okay? And every point on this curve has a difference between 2 points that's a positive constant. So do you remember how with our ellipse yesterday, if we measured to each foci and we added it together, it was going to be the same no matter where we were, okay? Same thing is happening here, except we're going to subtract the distances. So if I take this coordinate right here and I measure this distance and I measure this distance, the difference is going to be the same if I took a different point and measured the distance to the foci, and subtracted them. Okay, I could take another coordinate and I could take distance to the foci. Oops, that's not the foci. Distance to the foci, subtract them, and it'd be the same number. No matter which coordinate we pick on our curve, the distances to the foci have the same difference. You can now write this down. What? Blue today. Why? Well, green was parabola, right? Does everyone actually need one, or do you all need to take a picture? Or just put it back in my bed? Oh no. Okay, so when you're done writing this down, I have these cute little rectangles for you to paste into your notebook. When you're done writing what you need to from this, go ahead and paste in our standard form rectangle. And as you do so, you can start taking a look at it. Maybe you notice some things. Maybe you don't. Now you have actually graphed hyperbolas that open sideways. Do you remember graphing like y equals 1 over x, y equals 5 over x minus 2? Those kinds of graphs where we had like an asymptote, That, remember those? Okay, technically those are a hyperbola rotated, okay? These hyperbolas are going to be either strictly vertical or strictly horizontal, okay? So let's look at our standard forms and take in some observations here, okay? So first I want you to look at the equations. Notice how this looks very similar to ellipses. However, there's a couple of differences. First of all, we have subtraction. Okay. Second of all, since there is subtraction, okay, whichever variable is the positive one. So notice how in the horizontal one, x minus h squared is the positive one, and we're subtracting y. In the vertical one, y minus k squared is the positive one, and we're subtracting the x squared, okay? So whichever variable is positive, that's the direction that it opens. I need you to listen very carefully. A squared is always with the positive variable. It can be smaller than b squared. It doesn't matter. A is no longer strictly larger than b. In a hyperbola, a and b can be the same, a can be bigger, a could be smaller. But what's important is that a squared comes with the positive variable, okay? We are also, well, we have foci, just like we did with ellipses. Notice the formula now though. This time c squared equals, now it's a squared plus b squared, okay? Maybe you're worried about remembering which one is which. Your foci always need to be inside of your figure. So if your foci go too far outside of your ellipse, you know you found it wrong. Here, our foci need to sit inside of these curves, so they need to go past the vertices. Okay, so let's talk about how we put all of this together. So just like with an ellipse, we have a center. And that center is going to be plotted first. Okay, just like with an ellipse, our vertices are A away. So in a horizontal one, we'll move horizontally left and right, A, to get our vertices. In a vertical, we'll go up and down A to get our vertices. Now, you see a lot of dotted lines there, okay? These right here are actual asymptotes, okay? And that is what's going to give us our shape. We are going to have to plot these asymptotes, okay? Well, both A and B are going to help us figure out what the slope of our asymptotes are, okay? So what we're going to do is we are going to take B and we're going to plot points like we would in an ellipse. Like if I connected those four, it looks like an ellipse, right? But instead of an ellipse, we're going to create a rectangle. And what do you notice about the asymptotes? What are they in regards to the rectangle? At the, okay, well, we intersect at the center, and these go through the corners. These are the diagonals of the rectangle, okay? So if we use A and B to make this rectangle, we can plot our asymptotes through the diagonals, okay? Then with C, we find C and we plot our foci C away, okay? Now, with our hyperbolas, we are going to have to write the equation of our asymptotes, Okay, so I'm gonna kind of give you some hints here. So just like before, our vertices are A away, our foci are C away. We're still going to plot B away to draw our rectangle. Okay. When we write the equation of a line in with our asymptotes, I want us to remember what point slope form is. Point slope form is y minus y1 equals slope times x minus x1. We're going to go ahead and use that form to write the equation of the line. Once people have written down what they want, I'll talk about why that's going to be helpful for us. When you look at that blue rectangle that you pasted into your notes, look at the asymptotes. What point do both asymptotes go through? The center. That's convenient. Okay, so our asymptotes go through the center, which means we can take this x1, y1 coordinate and we can punch in the center. Okay, since both lines share that one point, we can put it in. All right, then our slope, we're going to look at our rectangle and we're just going to count rise over run. Sometimes it's going to be B over A, sometimes it's going to be A over B, just depending on if it's vertical or horizontal. I don't want you to have to like worry about remembering which one is which. I want you to just look at the picture. Okay. We're going to do 2 examples so we can really figure out how this all comes together. Okay. Are we ready? I need to see more smiles. Come on. All right, so here's our first one. What? In this one? So like A is going to tell us how far away the vertices are, and B is going to tell us how far away to make those B coordinates to make our box. You didn't buy that?
A always tells vertices.
Yes. Okay, so here's our first hyperbola. Man, this is nice, isn't it? Grayson, where's our center? Almost like too nice of me. Okay, so right now, I want you to decide at your pod, is this a vertical or a horizontal hyperbola? Ready, set, go. Okay, Owen, vertical or horizontal? Horizontal. John, why is it horizontal? Yeah, the x squared is positive. I don't care if 25 is bigger than 9. That doesn't matter anymore in hyperbolas. Ellipses, it matters. Hyperbolas, it doesn't. Hyperbolas, it's whoever's positive. Okay, so we have a horizontal hyperbola. So this is a squared and this is b squared. All right, so we're getting that a is 3 and b is 5. So when we want to plot our vertices, we want to go horizontally a. So I'm going to go horizontally 3 from our center to plot our vertices. Okay. B. We are going to use B sort of like we would in an ellipse. B is associated with Y. So I'm going to go up and down B, but we're going to do this really lightly. So I'm going to do this in orange because orange is like my light color. Okay. And then what we're going to do is we're going to make a really, really light dotted box that uses our vertices and those B coordinates that we just plotted. Okay. You're going to make it really, really light because it's not actually a part of your graph. Okay. What happens is our asymptotes are going to go through corner, center, corner, corner, center, corner. So let's go ahead and draw those asymptotes. And these can be a little bit darker pencil than your box. Now, when we name our asymptotes, we are going to use point-slope form. So I've written point-slope form up here. What did we say the point was that we were going to use every time? The center. So I'm going to go, whoops, x1, y1, and I'm going to replace it with the center. Okay. Then I'm going to look at my picture. So I can look at the rise over run. So I'm going to go from center to corner. What's our slope for this one? 5/3. What's our slope for this one? Okay, so one of our asymptotes has a slope of 5/3. One of our asymptotes has a slope of -5/3. So I'm just going to write two equations in one, okay? One slope is going to be the exact opposite of the other. So if one's 5/3, the other one's -5/3, okay? So our two asymptote equation lines are going to look like this. Hard part's over, okay? Ask me a question if you have it. We still haven't even like made our shape, have we? We decided that this was a horizontal hyperbola. So I'm going to take our vertices and our asymptotes are going to give us our shape. So I am going to approach the asymptotes. The asymptotes give us our shape. Okay. The asymptotes tell us how wide or narrow to make it. Because that's like what an asymptote does, right? Our curve approaches the asymptote without crossing it. Okay. Okay, we're missing something though. What haven't we done yet? We haven't done the foci. All right, so remember for a hyperbola, c squared is a squared plus b squared. Ew, what's 9 plus 25? So c is the square root of 34. Okay, well, 34 is almost what perfect square? 36. So the square root of 34 is almost 6. Okay, so I'm going to go 1, 2, 3, 4, 5, almost 6 for my one focus. 1, 2, 3, 4, 5, almost 6 for my other focus. Since we have a horizontal hyperbola, we are moving our foci horizontally from the center. And we'll give them a name. Plus or minus radical 34. In both our ellipse and our hyperbola, the foci are C away. In both hyperbolas and ellipses, our vertices are A away. All right, what questions can I answer for you here? What?
Like, yeah, we just get, instead of like the formula, we get like numbers, how much goes to the.
Oh, like this right here?
No, like if it's like in this form, like the fractions and stuff, but instead of the ages, it's numbers. How much goes to know if it's a hyperbole or
Because there is subtraction. If there's subtraction right here, it's a hyperbola. If this is addition, it's an ellipse. Is that what you're asking me?
yeah.
Okay, okay. So the focus or the foci give us that geometric property. Okay, so a hyperbola is a hyperbola because any point you pick on our hyperbola, if you take the distances and subtract them, it's the same as if you pick another point and do the same thing. Okay, so it's just signifying that geometric property that makes it what it is. Okay, now here I have one that's not in standard form. And Nick, I hope we can continue to answer your question once this is in standard form. Okay. Go ahead and write this down, and I want you to think about how we would know that this is a hyperbola. Well, we do things with them in calculus. I can tell you that. But like certain, like parabolas and ellipses are a little bit more applicable than a hyperbola. Okay. But like certain things are parabolic shaped, certain things are ellipse shaped. Okay. Hyperbolas. Yeah. Out of the 3, hyperbolas aren't as exciting. Okay, so how do we know that this is a hyperbola? First of all, we know it's not a parabola because we have both variables squared, x squared and y squared. Second, we know it's a hyperbola rather than an ellipse because one of the squared variables is positive, one of them is negative. So when we do all of our completing the square, we'll have that subtraction in between. Well, we're gonna have to, yeah, which will give us the subtraction. Okay, so let's talk about how we would complete the square. 16y squared, that 16 is going to have to be factored out of the y squared and, oh man, what do you get when you factor 16 out of 64y? Oh, good. You are on top of it today. Okay. When you are completing the square for a hyperbola, your second squared variable is going to have a negative coefficient. That negative has to be factored out. And when I factor out a negative from a positive, it's going to change it to a negative. Please be careful when you factor out this negative that you also factor it out of that second term. And then I'm going to subtract 47 and add our two mystery numbers. Okay. Okay, what completes our square right here? B over 2 squared gives us 4, but we're not really adding 4. We're adding 4 times 16, which is 64. What completes our square right here? 1, but we're not adding 1. We're adding 1 times negative 1. What's 64 minus 48? Okay, so just like in an ellipse, we need this right side to equal 1. So we are going to have to divide both sides by 16. We have y plus 2, the quantity squared, over 1, minus x minus 1 squared over 16 equals 1. There is our hyperbola. Okay, so Nick, do you see what I mean? How there's subtraction in between versus addition? Okay.
How did you get y plus 2 from y squared plus 4y?
So y squared plus 4y plus 4 factors to y plus 2 times y plus 2.
Okay.
So we write it as y plus 2 squared.
Okay.
Okay. Our center, please be careful. Where's our center? 1, negative 2. Please take the x first and then the y. Okay. Bella, is this a vertical or horizontal hyperbola? Why? Okay, the x is negative, the y is positive, so we have a vertical ellipse. So hyperbola, we have a vertical hyperbola. So 1 is our a squared. 1 is our a squared, 16 is our b squared. So our vertices are going to be vertically up, down, up one, down one. So our vertices are at 1, -1, and 1, -3. Our B value is 4. And our B value is with X. So we're going to move horizontally 1, 2, 3, 4. 1, 2, 3, 4. Very lightly make those coordinates so that we can make a box with them. Okay. B was 4. So I moved horizontally 4 to make our rectangle. And the purpose of that rectangle is so that we could make these awesome asymptotes. When we write the equation of our asymptotes, we are going to use the center. So our center is 1, -2. And then rise over run, what's our slope? Plus or minus 1/4. Rise over run is 1/4. Oh, this is a super wide hyperbola, yikes. Okay, and then our foci, C squared is A squared plus B squared. So C is the square root of 17. The square root of 17 is just a little bit bigger than 4. So I plotted my 2 foci a little bit more than 4 away. And since I went vertically, I took my center and I added or subtracted radical 17 to the Y value.